Yesterday, Saturday, as always with our conference, Saturday is always the day where we pound science into your heads. And then Sunday is the day where it's not completely devoid of science, but we're much more relaxed and much more sort of open your mind, and let's talk about some things that really wouldn't have been in the lexicon yesterday. And in that realm of sort of getting a little bit more out there and opening your mind to some other things, you know, a lot of folks probably can realize exactly how integral that mindset is to a lot of the things we do here. I mentioned Dave Talbot. His entire life's work has been about following what truth he saw, having an open mind and not worrying about the pushback, and really blazing a trail. We all heard Pierre-Marie Robitaille. Dr. Robitaille spoke twice yesterday. When he received pushback on some of his theories on the sun and wasn't able to gain any traction whatsoever, he took out an ad in the New York Times. That takes... We're starting to see that this is the kind of people, this is the kind of mindset we look for. Also, I know many of you have seen that John Coleman is in the crowd this weekend, the founder of the Weather Channel. And that is absolutely incredible. John, thank you for coming. And his story is not unlike that of Dr. Robitaille or that of Dave Talbot, in that there was a passion that got a hold of them. And despite the pushback, despite the barriers to accomplishing what they want to accomplish, just pushed through it and realized that right wins out eventually. And you know, some still in the process, some already done, but it's a matter of changing the world. John Coleman definitively changed the world. Dave Talbot and Pierre Robitaille are still in the process of changing the world. And so that sort of sets the tone for what we're going to talk about today. And we're going to start with one of my favorite topics, which I really only get to discuss on Fly on the Wall, really, because it doesn't really fit so much with the sun and the earthquakes and the weather, but it's the notion of life outside the Earth. Particularly interesting for me is intelligent life and its potential outside the Earth. And so a lot of folks know that I'm into this topic because I made it a point to say it about 5 different times in some of the Starwater videos, that the reason why I thought this whole Starwater principle was so interesting was because of what it implied for life out there. And so this is a topic that some folks still see as very, very fringe, and that's one of the things that I hope that we can serve as an antidote to here today. So this is Adrian Deo from the Suspect Sky channel.
Good morning, folks. I'm Adrian. Ben and I grew up together, been friends for a while, and been kind of on this journey for a while together. From Pittsburgh, still live there. I haven't made it out to New Mexico yet. But yeah, I run the Suspect Sky YouTube channel, Fly on the Wall podcast member, and I help out with the website and some of the research and stuff. So yeah, looking forward to having our talk today.
Absolutely. So what we did is we were taking questions from folks, whether it's on email, YouTube. A couple of folks ran up to me at the beginning of the conference and said that they wanted to make sure they got questions in. We took in about 55 questions, and I've narrowed them down to what I think would be the best discussions for this. If we happen to get through it, we'll have some more time for questions here, and if not, he's one of the only guys wearing a suit, so he's not hard to find. So let's just get started. I'm going to basically be asking the questions, and then he'll sort of lead the discussion, but we'll kind of go back and forth. So here's the first one. The topic of extraterrestrials is one that remains somewhat fringe today. It's thought that people who are really into this stuff are out there as the things they're looking for. But there are some very serious people taking the search for life outside the Earth very seriously, and they want to know if we could break down some of the voices who are speaking up on the topic recently.
Sure. And this has been a really exciting thing for me because, in particular, I've been following the fast radio burst phenomenon for about 4 years now, I think. It was my inaugural presentation at the first Observing the Frontier conference where we discussed just sort of the strange attributes that fast radio bursts have and also some of the interesting mathematical properties that they exhibit and their potential to be an artificial signal. And it was very gratifying that just a few months ago, 2 Harvard physicists published a paper where they analyzed the properties of fast radio bursts and some of the engineering principles that would be involved with producing a signal of that strength and what it might be used for. And these Harvard physicists suggested that perhaps fast radio bursts could be used to propel interstellar probes on solar sail vessels. It was a really interesting theory, and what was so exciting was they looked at it in 2 regards. The first is they looked at the energy parameters of a fast radio bursts, how intense they are, the types of frequencies and other qualities that they exhibit, and they discovered that in order to produce a signal with the energy characteristics of an FRB, you would need a reflective disk that would harness the energy of their stellar host about twice the size of the Earth. And then they looked in a completely independent scope, they looked at what are the engineering principles involved in producing that amount of energy. And it turned out to be, coincidentally, the exact same size, a reflective disk, twice the size of the Earth. So it's a really exciting coincidence that occurred that lent some credence to the possibility that these could be artificial signals. Another really fascinating observation that these physicists made was that FRBs, when they come in, they sweep across us in milliseconds. And the physicists suggested that this might be as our galaxy rotates relatively to the galaxy where these signals are being produced, we would get that exact same sweeping effect. It would be a really quick, almost like we were in the line of sight for a brief millisecond as it swept across the Earth. And another really interesting thing that they discovered was that the FRBs, on average, come in at 1 gigahertz frequency. Most of them come in at 1.4 to 1.5 gigahertz. And the physicists noted that the optimal frequency with which to propel a solar sail vehicle would be 1.5 gigahertz. So there was all these really interesting coincidences and sort of independent parameters that they coincidentally matched up that lent a lot of credence to the possibility that these were artificial. And it was really validating for me because this is Harvard. This is not some random publication. These were Harvard physicists taking these bizarre signals that we've been receiving, that there are no known astronomical phenomenon that can produce them, and they were taking it very seriously. So that was really exciting. And then there's been some excellent work by a physicist in Canada called Barrow, I think I'm pronouncing it right, Barrow, who discovered 234 sun-like stars where periodic pulses of laser beams are being received by the Earth. And so what this physicist did is he took the digital Sloan all-sky survey, which included 2.5 million stars, and he used Fourier transform analysis, which is a method by which you break down a frequency signal into sine and cosine contributing elements. So you break the signal down into core components. And what this does is it lets you discover frequencies that are hidden in those signals. And what he discovered was there was laser pulses that periodically appear at consistent time intervals, and these were coming from 234 sun-like stars. And the most exciting thing about the article to me was that statistically, if these were natural origin, you would expect these sort of pulses to come from a wide distribution of stars, from stars, not all sun-like stars. So I think that lends a really interesting piece of evidence to, why are these signals coming from sun-like stars. And there is a natural possibility, and these would be high-intensity stellar eruptions, but the the pace at which the pulses were received, this physicist believed was unrealistic to be natural, that the stellar eruptions couldn't occur that fast. So.
Yeah, I definitely wanted to make sure we remember when we're talking about this one. Do you remember it said that the direction that the laser-like emissions that were at the same power and focus that human laser technology could be at like in 100 years, they were all firing at the other sun-like stars that were also firing these things out. So it's almost like it was a communication network. The sun-like stars were only making those emissions in the direction of the other sun-like stars that were also making those emissions.
Yes, absolutely. And another really interesting component of that is that they all have the same rate of pulsation. And so this physicist felt that this could be an indication that if you fire a laser beam at your component or your target, that if you matched the rate at which you would receive that signal, this was a way to indicate that intelligence was communicating with one another.
Interesting. You talk about Dr. Lund really fast?
Oh, sure. There's another interesting article out there by a physicist named Dr. Lund. This comes from the Vanderbilt University. And he did sort of an imaginative article whereby he laid out the parameters by which Earth could receive and detect and identify a signal of an alien megastructure destroying another Earth analog-sized planet. So this is kind of the Death Star, sort of a concept. And he lays out, this could be for war, this could be for mining. So he lays out a couple reasons. But then he goes through the characteristics of what a black body radiation signal that we would receive, what it would look like, and how we could identify it as an alien megastructure involved in this sort of destruction activity. But what was interesting about it was that he mentioned that the LSST all-sky telescope will go online in 2020. And his point was that astronomy is sort of a collect as much data as we can type of science and then figure out what we found. And his point was, if here are the parameters to discover activity such as an alien megastructure destroying a planet. So here's what we would look for, here's what we would find, and we're going to be capable of finding this type of activity in 2020. And he mentioned that further research should be done to say what other kinds of activity could be discovered of alien activity using these sorts of new all-sky telescopes. So it was a really interesting idea.
Yeah, it is really fascinating to see some of the voices and that are talking about this, because you realize it's not just some of the folks in our community and I would say offshoots from the online community that tend to be a little less fact rigorous. It's not just this. I mean, the Center for Astrophysics at the Harvard-Smithsonian Center, they have no jokes about this whatsoever. The number of articles they're publishing about this is preposterous. Dr. Lund is very much, it almost reads like he is expecting something to be found very, very soon. And he's one of their top guys in the space world down at Vanderbilt. So it's really interesting that, even I have to admit that when I see certain videos on YouTube, I begin to think, here we go again. But there are some very, very serious people who have done very, very hard, rigorous work throughout their lives, and these are very smart people, and they're taking this really seriously. They really are. This next question is my own. Sorry, but I get to put my own one in here. All right, so Adrian, since you and I have been friends for 20 years this year, I happen to know your hypothesis on the Drake equation, and I think everyone else should. But you've recently had a lot of evidence, more so than when you first laid it out to me, that now bolsters your claim that the Drake equation and more accurately some of the popular numbers put in for some of the variables in the Drake equation was inadequately representing the potential for life out there. And so I'd love to talk a little bit about that, maybe habitable worlds, moons, things like that.
Yeah, and I think you summed it up really well there. For those that don't know, Frank Drake, it was the founder of SETI, and he came up with an equation that could be a mathematical tool to visualize and estimate the number of potential alien civilizations currently existing right now, today, that could be radio communicative with us. So a number of the variables include the rate of star formation, the rate at which planets form around stars. And then you get into some speculative stuff such as the probability that life will form, probability that life could be intelligent, and the lifetime of those civilizations. So those are all speculative, but the point of the equation is here are the variables that we need to learn more about in order to estimate ever better into the future. And this was done in the 70s, and we've had a lot of time to sort of learn a lot more about our cosmos, and we've learned a number of things. So we know the rate of star formation pretty well, so we have that down. But what has been only sort of recently, in the past decade or so, has been that exoplanets are the norm. So for a long time, we thought that maybe planetary formations, such as our solar system, might be exception to the rule. We know that that's no longer true. Planets seem to be the rule and not the exception. Along with that is that Drake did not consider exomoons. So we believe that there's going to be a lot of evidence that exomoons should be added into this equation. So even if a planet might not be in the habitable zone, the conditions of the exomoon might be habitable for life. So that's another variable that needs to be added into the Drake equation that doesn't exist currently. Another really interesting pursuit of study is out of Russia. There's a physicist who did a paper on the habitability of circumbinary planets. So this is a really interesting article that talks about how binary solar systems are actually more favorable to life than non-binary star systems. And this is for a number of reasons, including planetary formation in the habitable zone. So because of the gravitational effects of the two stars, planets tend to form in habitable zones in binary systems more often than they do in non-binary star systems. There were other reasons as well, such as binary star systems are better at shielding from radiation. Binary star systems are better at producing tidal effects in seasons. And there was a whole bunch of other reasons. But what was interesting is that he makes the point that life on Earth is actually an accident, and we're actually an exception to the rule. And it's because our unique solar system exhibits properties of a circumbinary. For example, we have Jupiter and we have the Moon. And those two contribute to the factors that would sort of mimic a binary star system. So we're actually pretty lucky to be here. And his point was that if we're the exception, then perhaps the Drake equation needs to be updated to consider the effect that binary star systems, particularly M-dwarf star systems, constitute about 40% of the Milky Way galaxy. And he refers to these as life breeder solar systems. So we need to consider that when we think about the probability that life might be out there. So in a couple years, the James Webb and the TESS telescope are going to be deployed, and they're going to be able to study the atmospheres of exoplanets and look at and detect and analyze organic and life signatures of atmospheres, things like carbon, things like oxygen. And a lot of work is done in the field on reducing the amount of false positives. So we don't want to think we detect life on a planet and turns out to be false positive. But this paper was interesting in that they discussed false negatives. And the idea behind this is that there are going to be ocean worlds that have a number of microbial organisms producing a number of gases that will actually make the planet appear to be inhospitable to life when actually it is hospitable to life. So his point was we need to keep in mind that these false negatives should be statistically considered. And my point is that when these telescopes launch, this might affect the Drake equation, and we should be considering that. Another interesting point was the snowball Earth, right? So we're going to detect planets that are in ice age periods. But we're getting that light 1,000 years later because they're 1,000 light years away. And while those will be considered today as inhospitable to life, they might presently be hospitable to life because of the ice age program, or the ice age process going from ice age to non-ice age. So we need to consider that whenever we're considering the statistical possibility of life out there.
Yeah. A good way to think of that is many folks have heard the common number Whether it's right or wrong, let's just assume it's correct that the Milky Way galaxy is 100,000 light years across. And let's say, we're certainly not all the way out at one arm, but let's just say that there's a civilization 100,000 light years away on the other side of the galaxy, and they can see us. Theoretically, they're looking at our ice age. Our last ice age is what they're looking at. Earth doesn't look too friendly. And so when we look out there and we see an ice world, who says that that hasn't become like Earth today? Which is, when you start thinking in terms of that, you really begin to start to blow up this number here. All right, let's go on to the next question. Oh, right. So this one is about fast radio bursts and some of the other ones as well. This person wants a quick explanation. I thought this was a good one. You kind of already described a little bit about what fast radio bursts are. But what are some of the things that really make them worth noting? And, some of the things we haven't mentioned yet, like maybe talk about how some of the natural explanations are dwindling, how they're mostly transient, things like that. Just some of the other basics as sort of like a review from the Pittsburgh and Phoenix conference.
Sure. So there's been 29 fast radio bursts detected to date. 17 of them are one-off events. 2 of them were repeating. This is called the double pulse FRB. One came in right after the other one. And then there are 10 FRBs coming from an area of space that is repeated 10 times. So they're really bizarre. And an FRB is an extremely powerful burst of radio energy that lasts for a millisecond, maybe 2, maybe 3. In FRB, the signal doesn't arrive all at once. So the first part of the signal will arrive, and then a millisecond later, the rest of the signal will arrive. And that difference in arrival time is called dispersion measure. And this measurement is used to estimate the distance that it has traveled in order to reach us. They all have really high dispersion measures, indicating that they all appear to be coming from billions of light years away. The 10 that repeat, though, is what really makes this interesting, because the natural origin hypotheses, most of them covered things such as cataclysmic events. These are things such as black holes colliding, asteroids hitting neutron stars, producing highly energetic releases of signals. But the repeating ones sort of discount that cataclysmic concept that it might be a natural origin theory. Now, there is a possibility that FRBs are produced by different types of events. So it is possible that the repeating one is a different source than a non-repeating one. But the natural origin source is dwindling. So there's been the real-time fast radio burst, which I believe was completed in 2015, was the real-time observation of an FRB actively happening by multiple telescopes on the planet, which generally confirmed that these appear to be coming from very far away, which eliminated some of the near source theories. And then some of the current ones is soft gamma repeaters, but these don't work for a number of reasons, particularly because they're accompanied by gamma ray radiation, which we don't detect accompanying fast radio bursts. There's a possibility that these are produced by pulsar nanoshots, which is actually an interesting concept where a pulsar is impacted by some other astronomical body, and as the pulsar slows down, it releases bursts of energy that are very high intensity and would appear like FRBs. But what's interesting about them is that they should repeat and they should slow down over time. So the non-repeating ones don't really fit this model. There's another possibility, which is that they are asteroids colliding with neutron stars, which is very similar to the nanoshoot concept. But again, these ones shouldn't repeat, as we often see, unless there's some really statistical and probable events occurring.
And speaking of things that should not occur, the next question I'll just sort of paraphrase, and you'll know it's your question, who put it out there. So In the Pittsburgh and the Phoenix conference, we were looking at some of the dispersion measures that were coming along with these fast radio bursts, and some very interesting looking math that it is actually hard to really know what to make of it. And so we have spent the better part of the last year trying to figure out how we really should be looking at these fast radio bursts to tell if there is anything that is not random. Is there some kind of pattern to these? And this next chart is something that Adrian and I made. Hopefully you guys can see the blue line and the red line on there. I know it might be hard against the black. But essentially what this was, and Adrian, correct me if I say this the wrong way. So this took the dispersion measure, and I eliminated the 10 times repeater because that one is just, it's different than the other fast radio bursts in so many ways. And so this was the 17 or the 18 other ones right here. And this is how close their dispersion measure was to a whole multiple of 187.5, which you might remember was this weird pattern that some of the scientists were saying existed amidst these dispersion measures. And so you can see down there at the bottom, we have five columns that these dispersion measures could fit into. Either the dispersion measure was less than 0.1 away from a multiple of 187.5. It was the next column is it was within 0.2, 0.3, 0.4, and the furthest away you can be from a whole number is 0.5, so that is indeed the last column there. Now, the red line is what we expect. If these things are random, it doesn't matter if they're coming from thousands, millions of light years away, or they're coming, or they're being produced by an electric double layer, and it's maybe halfway to Mars. Regardless of which one of those it is, these things need to be random and distributed all over if they're natural. So what I mean by that is, let's say we were looking at solar flares, and we would get, C-class flares, M-class flares up to M2, but we never had an M2 to M9. And then all of a sudden we had X flares, and there's just like this gap there. You might start to say, well, there should be sort of a nice even distribution. It should be nice and evenly distributed across everything. So if we're looking at the dispersion measure of fast radio bursts and how close it is to a multiple of 187.5, it should really just be randomly distributed, which is the red line. But that's not what we find. We find that, in fact, these things are very much loaded towards the multiples of 187.5. And while it's very difficult to understand what the practical meaning of this is, how can we use this to describe something about either fast radio bursts or their genesis? That's a little bit more difficult. But what is not difficult is to look at the distribution of the math of these fast radio bursts and say, the math that we're looking at right here should look like the red line. Now, granted, with just a sample of 17 or 18, okay, maybe it should be a little bit wavy. But it should not be this front-loaded. And it's looking like, even with only 18 samples, this is still significant to the 99th percentile. And so there is something about the math of these fast radio bursts. And sure, this could be something to do with their genesis, or it could have something to do with how they interact with our technology or our solar system or how we detect them. But there is something not random like you would expect in nature, which would be the red line here. There is something, and it doesn't necessarily mean aliens. It might mean that there is something about our solar system or our magnetosphere or something else that puts this pattern into the dispersion measure, but there is a pattern. These are not random numbers. There is some kind of a pattern in the dispersion measure that sets these peaks to where you can find them. So you can find them with a dispersion measure about 187.5, and then again at, what's that, 370? Is that something like that? And you don't find very much in the middle where you really should see these things dispersed all throughout the chart. You see them on the 1. You see them on the holes. And that's very, very interesting, and it should not be that way.
One interesting thing, and I'm glad you brought up the math, is that the first 10 fast radio bursts came in at equal multiples of 187.5 of dispersion measure. And when you think about that, that means they're equally spaced apart from Earth. So we're talking 2 multiples away, 4 multiples away, 8 multiples away, 10 multiples away. So if you think of a graph, this is a diagonal line with 2 or 3 fast radio bursts coming in at 2 times 187.5 distance-wise, 3 coming in at 4 times 187.5, 2 coming in at 3. So even the Harvard physicists mentioned that this looks like beacons, almost like they're equally spaced beacons.
Adrian Deo, everybody.